Alright, we did a lot of things with this particular table. This is a slightly extended version of the table that you saw before in earlier slide. But to what end? What we did was we made a project network, we calculated how long the project takes to complete, we found slacks and all these things. The first thing that should be obvious, but let me explain this here a little bit, is if I ask you how long does this project take to finish, right? Finish. The answer is not. So if this is the normal time to finish the project for each activity, the answer is not adding all these up. It's not. Because some of the activities can be overlapped, right? So the time it takes to finish the project is given by the project network that you made earlier, and at the end of the project network, the last activity, its earliest finish or latest finish, those are both same. That number is how long it takes to finish the project. In our case, it was 22 weeks. So if I ask you how long it takes to finish the project, don't add this all up and give me that number. What that is assuming is you're working one project after another and there is no overlap. How long it takes to finish the project is 22 weeks. Right? That is the first takeaway from this project network exercise that we did. The second thing I might ask you, what is the cost of doing the project? Right? This was our normal table. Our normal table had this column, this one, and this one. These other two are added tables. These two are added, and I'll explain what they are in a bit. And if I ask you how much it costs to do the project, now in that case you have to add all them up. Don't just add the cost of the activities in the critical path, right? Another way of finding how long it takes to finish the project is you add the processing time of the activities in the critical path. So you know what your critical path is, and then you add the processing time in the critical path. That is same as looking at the earliest finish or the latest finish of your last activity. But to find the total cost, you have to add them all up, because you have to do each activity. Overlap or no overlap doesn't matter. The total cost of finishing the project is this. Right? Now I added these two columns, crash time and crash cost estimate. What this is doing each of these activities. Say activity A, people, managers or your client might have two estimates. The first estimate is, well, if we do in our normal speed, it will take us 3 days and it will cost us $1,200. But we can crash as in squeeze it or do it faster in 1 day, but that will cost $2,000. Right? Some other activity, like say activity F, the normal it takes 3 weeks, but even if we crash it, it takes 3 days. That means we can't crash it. Another way of saying it. There is one more part to this. We assume a straight line change, just like in accounting, there's this straight line depreciation. So if we do it in 3 days, it costs $1,200. If we did 1 day, it costs $2,000. That is, there is a gap of $800. So if I ask you, how much does it cost if we do it in 2 days instead? I mean, again, it might not always be true, but we kind of assume this. Remember, going from 3 to 1, it costs us extra $800. So that cost of going from 3 to 1 or reducing by 1 week, 1 unit, is 800 divided by 2. That is 400. Formalizing this, I have written the formula for you. The crash cost per unit of time is crash cost, that was 2,000, normal cost, that was 1,200, normal time, that was 3 weeks, crash time, that was 1 week. So 2,000 minus 1,200 divided by 3 minus 2, so it is $400 per week. Okay, it costs you $400 to reduce the time by 1 week for that activity. So what we can do is we can calculate this crash cost per unit of time for each activity. So in this case, the first activity, we know that it costs $400 per week. It costs $400 per week to crash, 400 per week. For B, you go from 5 to 3, there's a cost of increase of $1,000, so it's 500 per week, and so forth. You can do the calculation. I did this for you in the next slide. So the crash cost for A is per week is $400. The crash cost for B is $500 per week. For C is $250 per week. D is $50 per week, and so forth. But activity F, H, J, and K, they cannot be crashed. F, H, J, and K cannot be crashed. Let's see. F, 3 and 3. H, 3 and 3. J, 2 and 2. K, 2 and 2. So those cannot be crashed. So okay, with that, that's how you read this table. With that in mind, suppose I ask you, well, normally if you did every activity in the normal time, it costs, you can finish this in 22 days. Okay, if I want to finish in project in say 21, or let's start with 21 first, and then we'll come back to 20. If I want to finish the project in 21 days, which activity do I crash? It's not an obvious answer, right? Because different activities cost different amounts to crash. So which one do I go about in crashing? The answer is pretty simple. There are two steps to this. The first step is you have to do the project network, find the critical path and so forth. And then you have to find the crash cost per unit time for each activity. Okay, you have to find the crash cost per unit time for each activity. Okay, and then you have already done the project network diagram and found the critical path. After that, what we can do is our critical path from our previous slides, we know is B, C, E, F, H, J, and K. This is our critical path, right? And this is where the critical path becomes important. If you crash anywhere else, that is not going to reduce your project completion time from 22 to 21. So we have to make sure, we have to identify our critical path first. This is our critical path. Now let's compare this critical path with what we have done, this crash cost per unit time. F, H, J, and K cannot be crashed. F, H, J, and K cannot be crashed. So they cannot be our candidate for crashing anymore. So our candidates are B, C, and E. Go ahead and choose the cheapest one among this. B is 500, C is 250, and E is 1200. That's why we choose C. That only adds our cost by $250. That adds our cost by $250, and we go from 22 to 21. Right? How does it look in our project network diagram we did? Well, we decided to crash C. So deciding to crash C is we go from 2 to 1. You go ahead and do this project network again. I'll guarantee you'll get this to be 21. Okay? Now you can repeat the process again to go from 21 to 20, and that's exactly what you have to do. You cannot crash this two at the same time, even if you had wanted to go from 20 to 22 to 20. After you have done this first step, reducing it by 1, go ahead and do the forward pass, backward pass, identify the critical path, and go ahead and calculate the crash cost per unit of time for each activity. In this case, now C cannot be crashed anymore, so C is going to come down to this list. You identify your critical path and choose among the critical path which can be crashed, the cheapest one. Okay, so the question I could ask you from this is, you already identified what is the total cost of doing this project. That was the sum of all of this, right? The sum of all of this. If I ask you, if you are going to do the project in 21 weeks instead of 22 weeks, what is the total cost? Well, you have to inquire all these costs plus that extra $250 that you added to do it in to reduce that 1 day of time. So that would be your new cost if you want to do it in 21 days. Okay, that was our first intuition that you can take away from this CPM method, a critical path method. Okay, let's revise this again. What we did, we started with making the project networks, and then we extended our table a little bit to add this crash cost, and crash time. The story was each of this activity, some could be crashed and some could not be crashed. Sometimes we are given this crash cost, and then we can get the difference between this crash cost and the normal cost and divide by the difference between the normal time and the crash time. And a slight disclaimer here, these days you will see problems, instead of just giving the total crash cost estimate, they give you how much it costs to reduce the activity time by 1. So instead of saying 2000 here, they might just say what we usually calculate, 400 per week, and you can only crash up to 1. They might give you that number, so be aware of that. After we calculated that crash cost per unit of time, what we did is we put those together. We put those crash cost per unit of time in one side, and then we put out our critical path on the side, and we said, look, some of these activities in the critical path cannot be crashed, and then among the remaining activities we choose the cheapest one. Again, one interesting thing here, there is no value in crashing an activity that is not in the